All right, everybody, so we're going to go ahead and get started. Just so we're aware, we are recording our lectures. The sound might be a little scuffed for this lecture because I couldn't get the microphone to work on the computer this morning, so I'm having to record the sound on my phone. And later I'll put that overlapping with the video and all that, but just know the sound quality might not be crystal clear. It should still be something that we can hear. And I'll post the video on Canvas after class. I'm not going to do live Zoom sessions for you to stay at home and watch, because I do think that the priority should be being in class. But in case you need to go back and see, like, hey, what happened in class? You want to revisit some material, you should have it available to you. All right. So, as a reminder, we have our first homework assignment that's going to be due next week on Wednesday. Our first homework assignment is going to cover pretty much the material that we're talking about today. And that material is going to be on the discussion of physical quantities and specifically relationships between quantities. And we're going to talk a little bit about these quantities of scalars and these quantities of vectors. So we're going to delve a little bit into the introduction of physics. Now, some of this might be review for those of us who have taken more advanced physics classes before. But if you have any questions, no matter how small, be sure to ask as soon as possible. Don't hesitate to interrupt me. Yes?
Is there notes like on Canvas that we can look at, or just everything is in the lecture?
I put resources on Canvas that are links to various web pages and textbook chapters that are relevant. I don't put my notes on Canvas because I don't think my notes are particularly useful when it comes to studying. My notes are very broad, I would say, and leave a lot out because, again, I'm working out a lot of the stuff at the board with you guys. I don't do lecture slides, so there are no lecture slides for you all. But my way of giving you access to what would be lecture notes is giving you access to the video, so you can go back and watch it. Any other questions? All right, so let's go ahead and start off. Today we're going to start with this idea of physical quantities. Quantities are physical characteristics that we can assign numerical values for. And as we go throughout this class, we'll see tons and tons of physical quantities that we will be working with. And some of the biggest ones that we'll see are things like length. Length is a physical quantity. Length describes the distance between any 2 points. And that's going to be one that we spend a lot of time studying. We've seen this one in lab quite a bit in this first week. Other physical quantities that might exist, well, we've seen mass, right? We've seen mass in lecture. Mass is a physical quantity that describes how much matter exists in an object. Other physical quantities that we might see, well, you walk out of this hall after class and you'll notice it's really hot. We might say it has a high temperature. Temperature is a physical quantity. There are tons of physical quantities. You have stuff like speed and velocity, acceleration. Each of these describe a different physical characteristic. Now, when we talk about these physical quantities, it's not just a discussion of wanting to know about, the mass of an object or the length of an object. If we end our analysis of physics at that basic of a level, well, we haven't really done much, right? We've taken a measurement. No, instead what we like to do is see how different physical quantities relate to one another. So we take these physical quantities and we see how do they relate to each other. And we might see how they relate to each other in terms of maybe taking 3 length measurements and finding a volume from that. We might find from length a volume. What did we do there? We took a base unit of length, something we can measure directly, and we calculated a derived volume. So we find these derived characteristics, these derived quantities. From our base quantities, we can derive further quantities, such as volume. We might see, well, how might volume and mass be related to each other? Well, we saw this in lab. We saw that volume and mass relate to each other and give us this new quantity of density, a newly derived quantity of density, which tells us about material. So what we want to really do in this class is see how all of these physical quantities that we will investigate how they relate to each other, because all of these physical quantities, they are related to each other. And when we start investigating these relationships, we start to understand that as we increase one thing, something else might change. So when we look at relationships between different physical quantities, changing one thing might change another. For example, we imagine having two objects. We imagine having perhaps a cube of aluminum. Here's our cube of aluminum. We might say this cube of aluminum, well, has some volume, right? Say this cube of aluminum has some volume. You can find by taking the length, the width, and the height, multiplying them together. That gives you this volume. Well, what happens if we take this cube and we cut it in half? So let's say we cut in half this cube, and we're left with a rectangular prism, a cubic-shaped object. But if we cut it in half, what have we done? We've decreased the volume of the cube, right? So we've decreased the volume of the cube. We might say our initial volume is greater than our final volume. In fact, we can say it's twice as great if we wanted to. But we say we decrease the volume. That makes sense, yeah? No arguments yet. So if we decrease the volume, then we say, well, what changed about the cube otherwise? We might say, well, if we decrease the volume, then we've probably also changed the mass, right? We take our original cube, we put it on the scale, maybe it says 1 or 2 kilograms, whatever it says. We cut it in half, and the mass probably changed. And if you decrease that volume, how might you expect the mass to change? Should you expect the mass to increase or decrease? What do we think? You might expect it to decrease. You decrease the volume, you might expect that this decrease in volume, we might expect it causes your initial mass to be larger than your final mass. And this is what a relationship is. We say that volume should therefore be related to mass. The volume of an object should be related to the mass of an object. And we understand that there exists some mathematical way probably to describe this relationship. Okay, well, let's think about this a little bit more. Let's say we halve the volume. What can we say about this decrease in mass? Do we think that this mass will decrease by 1/4, an eighth? Do we think this mass will decrease by half? What do we think? Probably by half. Absolutely. We might expect the mass to decrease by half. So that tells us that there should exist some relationship such that the ratio of decrease of volume should be the same as the ratio of decrease of mass. All right. Well, putting this into more mathematical terms, we say since the decreases should be equivalent, that means there should be a proportionality. We should expect these things to be proportional to each other. So what we're going to do is we're going to say initial volume. Well, I don't want to write out initial volume all the time. So I am going to define a way to refer to initial volume without having to write out all the letters. I'm going to use a variable here. And I'm going to say initial volume. Well, I'm going to represent that with a capital V. And we use capital V typically for volume to differentiate it from terms like velocity. So initial volume, V with perhaps a subscript 0. And call this V naught. Initial volume, volume naught. Our starting volume. We also might refer to it as V subscript I for initial. In any case, we say this is my initial volume. Well, what about final volume? Final volume. Might make sense to say my final volume, I represent it with a V as well. It is the same quantity, same characteristic measurement. So how might I refer to it? Well, If this is V naught, maybe this is V1. Maybe it's the first in an iteration of changes that we make. Maybe we cut it in half again and get a V2. Cut it in half a third time, get a V3. Weld another chunk onto it, get a V4 and increased in volume. Whatever you do to it, perhaps we're doing an iteration of changes. So we might use 0, 1, 2, 3, 4 as a subscript to describe these iteration of changes. Or perhaps we might just say we are only making the singular change, in which case we only need a final and an initial volume. And with the same respect, we can do this with mass. We can say that we have some initial and final mass, mi for initial mass, and we typically use lowercase m for mass, but that does change from time to time depending on what it is that we're talking about. And we might have some final mass mf. And so we define these different masses, these different volumes, and we say these things should be related to each other. In fact, we should see, again, that the volume of an object should be proportional to the mass. This volume of the object should be proportional to the mass. So we use this mathematical symbol, the proportional to symbol, to say that our volume is therefore proportional to mass. And we know this because we expect that if we cut the volume in half, then we should get half the mass. That change should be equivalent in ratios. We have now a relationship. This gives us a relationship. And physics is all about studying these different relationships that exist between different quantities. Perhaps we might see a relationship between a mass of an object and a change in temperature. How many of us have taken a chemistry class before? We will have seen things like calorimetry. Calorimetry discusses how temperature and mass are related to each other. All of science, all of quantifiable science, comes down to these solving of relationships. So what does this mean? Well, if our volume is proportional to mass, we can then take this and say, well, if this is true, then we can make this an equality. And we make it an equality by inserting what we call a constant of proportionality. I'm going to rewrite this. I'm going to insert a constant here. So I'm going to put volume, and then I'm going to put a constant in here. What is this constant? I don't know. I'm just going to represent it with the Greek symbol rho. There's probably a hint of what this is. But there's a constant in here. And whenever we put in one of these constants of proportionalities, this is just a substitute for some number. Whenever we put in one of these constant proportionalities, it takes our proportionality and makes it an equality. And now we're able to use it to solve different problems. We can say, for example, that this constant rho has a given value. What is that given value? Well, algebraically, we take this and we say the value of this value of rho is mass divided by volume. You just divide both sides by the volume, and you end up with this constant proportionality. And this is the constant proportionality that we call the density of an object. Every object, if you take the mass and divide it by the volume, you end up with the density. Any object, when you take the mass and you divide it by the volume, you get the density. And what's interesting about this is that the density, because it is this constant proportionality, it does not change. It does not change. It does not care that we cut the cube in half. It does not care that the mass is changed. Because what is true? Well, this constant of proportionality is given by the initial mass over the initial volume. But equally, we can say that it is the final mass over the final volume. Mass final over V final. So we use this constant proportionality to determine this relationship. And we say, okay, well, what if we looked at a specific object? What if we said we had an aluminum Let's say we have an aluminum cube. Now we can use this relationship. We can use this relationship to start investigating different physical situations. we have an aluminum cube, and we want to know what its mass is, but oh no, our scale is broken in our laboratory, so we can't just put it on a scale. What are we to do? Well, what we can do is we can measure out the volume. We can measure out the volume of our aluminum cube and say our volume is maybe 100 centimeters cubed. Say our volume is 100 centimeters cubed, and then we say, well, I know what the density of aluminum is. The density of aluminum should be 2.7 grams per centimeter cubed. In lab, we found this. Well, we found roughly this value in lab. We can also write this as 2,700 kilograms per meter cubed. We should all be able to do that unit conversion after lab. And then from here, we can use this new relationship that we found. We can now use this relationship we found to find that the mass of an object is given by its density multiplied by its volume. And in this case, we take our 2.7 grams per centimeter cubed and we multiply it by the 100 centimeters cubed that our object is, and we end up with what? We end up with 270 grams. We find the mass of our cube simply by using this relationship between these variables that we found. We study these relationships because we can use them to determine different quantities in physical scenarios. We can make predictions. In other words, I predict that the mass of this aluminum cube is 270 grams. If we wanted to test our prediction, we take this, we take it to another lab that has a working scale, we put it on, and then we see it doesn't match up. And indeed it should. Any good relationship that we find in physics does a great job of actually making the predictions of what we would expect. Any useful relationship that we study is able to find these predictions and make these predictions. Do we feel okay about this? I need the sign-ups. So then we say, well, what other relationships exist? Well, tons of them. Tons of them. For example, if you want to get something to move, if you want to make something acceleration, you give it a push. You give it a force. And in fact, what we can find is that the force that you apply to an object is proportional to that acceleration, that change in motion. We'll see this when we get to Newton's second law. Well, what other relationships exist? Relationships exist all over the place in every branch of science. In fact, one very interesting study of relationships exists in biology where we see how different things scale in animals. And for mammals, for any mammal that exists, humans included, for any mammal that exists, there's a relationship that can be mapped for the basal metabolic rate. The metabolic rate is how much energy we use up just doing our day-to-day tasks. So the metabolic rate, how many calories do we burn, for example, in a day, just doing our average task? Well, as it turns out that basal metabolic rate, if I can say it, is proportional to the mass of an animal. And that should make sense. Larger animals probably use up more calories. If we think about an elephant probably uses loads more calories than a mouse does, right? A mouse probably doesn't need to eat that much. An elephant probably needs to eat a lot. So we might say the metabolic rate is proportional to the mass of an animal, or specifically a mammal. But it's not quite that easy, because it's not a proportionality argument. Instead, the basal metabolic rate is proportional to the mass raised to the 0.75 power. It's not exactly a proportionality, a straight proportionality. It's proportional to the 0.75 power. But just because there's that weird 0.75 power doesn't mean that we cannot create a mathematical relationship. Because what we can do is take this basal metabolic rate and say, well, that means that it must be equal to some constant. What is that constant? Well, I don't know. But I'm going to fill it in. I'm going to say that that constant has a value of c. We like to use c for constant. Why? Because constant starts with c. So basal metabolic rate is equal to constant times mass to the 0.75 power. And we say, well, what is that constant? That constant might be something we're interested in knowing, because if we know that constant, then we can determine the metabolic rate for any mammal, given its mass. So what is that constant? Well, that constant would therefore be equal to to the metabolic rate divided by mass to the 0.75 power. Camera change. No, it does not change, so I'll stick to this half of the board. So we say here's our basal metabolic rate divided by our mass, and that would give us this constant. So let's see if we can calculate this out. And to calculate this out, we will use the example of a mouse. A mouse will burn about 0.15 thousand calories. A mouse will burn about 0.15 thousand times 10 to the 3 thousand calories per hour or per day? Per hour. Yes. 0.15 times 10 to the 3 calories per hour. I'm going to make a note on this calorie in a second. And how massive is a mouse? Well, mouse is pretty small. A mouse would have a mass of about 25 grams. Mouse has a mass of about 25 grams, or 0.025 kilograms. 0.025 kilograms. Now we look at this and we say, well, 0.15 times 10 to the 3, that's a lot of calories an hour, right? And we think about, I went to the gym last week and it took me so long to burn 100 calories. How could a mouse be burning so many calories? Well, there's a distinction to be made, right? When we talk about nutrition, the calories in food or the calories we burn at the gym, we're actually talking about a kilocalorie. A kilocalorie is the calorie that we see on our food containers. It's the calories that we see on the treadmill as we go running. And 1 kilocalorie is 1,000 little c calories. So an important distinction to be made there. We're not talking about 150 calories of food that we would see on the nutrition packet. We're talking 150 of these smaller calories, these more scientific calories. So if we wanted to write this, we could say, well, 0.15 kilocalorie per hour. So it's actually not that much. Mouse doesn't use up too much energy. But in any case, we ask, what is that value C? What is that constant? That constant C is going to be of value 0.15, and let's use the kilocalorie for our units. Because why not? Kilocalorie per hour. And we're going to divide that by the mass. The mass is 0.025 kilograms. But not just the mass, but the mass to the 0.75 power. So we take that 0.025 and we raise it to the 0.75 power. Now, as we go through this class, I want to make sure that we're all confident using our calculators. So let's all break out our calculators, pull out our phones if we need to, and let's calculate out what is this constant. What is the constant proportionality that will tell us about something's basal metabolic rate? When you have an answer, throw up your hand. Okay. Starting to get a few more, All right, wonderful. What do we get? Right. 2.38, how many of us got 2.38? We get 2.38 as that constant, 2.38, and there are some units attached to that. What are the units? Well, the units are going to be kilocalorie per hour from the top of the fraction. And on the bottom of the fraction, we have a kilogram to the 0.75 power. Very odd units. Sometimes these constant proportionalities have very strange units. But we end up with this constant. Now, what use is this? Why do we care about this? Again, this gives us a relationship. These relationships allow us to make a prediction. What is that prediction? Well, one of my favorite animals is the elephant. The elephant, very different than a mouse. An elephant has a mass of, well, perhaps about 5,000 kg. Mouse, very small. Elephant, very big. Something we all know. And the question is, if we know the mass of an elephant, can we figure out its metabolic rate? In other words, can we figure out how many kilocalories per hour this elephant is going to be burning? So let's go ahead and figure that out. Well, from the relationship, the basal metabolic rate is equal to the constant of proportionality in our relationship multiplied by mass to the 0.75 power. And what do you know? We just calculated out that constant. That constant is 2.38 kilocalorie per hour, kilogram to the 0.575 power. Again, very odd unit, but don't worry, that 0.75 power is about to cancel out, because what are we going to do? We're going to multiply it by the mass of an elephant, 5,000 kilograms to the 0.75 power. So we take, essentially, 5,000 to the 0.75 power, we multiply it by 2.38. We end up with some number. What is the number that we get when we multiply 2.38 multiplied by 5,000 to the 0.75 power? One answer. 1418 was what you said? Any other answers? How many of us got 1,418 kilocalories per hour? How many of us got 1,418? How many of us got something different than 1,418? What did you get? 1415. That's probably a difference of rounding, if I had to guess. You get numbers that are similar to each other, not exactly the same. It might just be a case of rounding. So we might say 1418, 1415. Well, it doesn't matter. Because when we look at these numbers, we'll say 5,000 exactly. The constant was 3 sig figs. We probably want to round to 3 sig figs anyway, 1420. 1420 what? We always need a unit. 1420 kilocalories per hour. An elephant burns, by our estimation, using this relationship, using information found from a mouse, we determined that the elephant is probably burning about 1,420 kilocalories an hour. That's a massive amount. Again, I go to the gym, I burn maybe a couple hundred, maybe. So what does this tell us? Well, this tells us an estimation. What use is an estimation if we don't compare it to real life? And in real life, the basal metabolic rate of an elephant is generally between the values of 1,300 and 1,500 kilocalories per hour. Why the large range? Well, there's a large range in massive elephants. I used about the average rate, the average of a mass of an elephant. So you get about the average rate for our range of metabolic rates. Now this is incredible. This is powerful. We start to build these relationships that allow us to make predictions of an elephant based on a mouse. And that is our goal in science. That is our goal in science, to determine all of these different relationships between different quantities. And again, these relationships exist everywhere. Any two physical quantities are probably related to each other. Now, the relationship might be boring. You might get that the relationship is linear, in which case you double one thing, you double the other thing. Or the relationship might get quite interesting, when we start talking about these biological relationships. All right, do we have any questions, any thoughts, any comments? Take a second, take a breather. Yes?
So once you find the constant to one thing that's proportional, you can find anything else that's related.
Absolutely, and it's important to remember what's related here, right? This is defined for mammals. So you put this against an alligator, you probably won't get the answer, right? It might not work for reptiles, it might not work for fish. But it works well for mammals. So this constant works for mammals. When we talked about density earlier, we had that constant proportionality of density, rho. With that constant, well, that was true for any material of the same type. So you talk about like comparing 2 chunks of aluminum, 2 chunks of iron, 2 chunks of lead, 2 chunks of wood, whatever it is you're looking at. You want to make sure that you are talking about 2 things that are of the same type. In this case, mammals. Earlier it was aluminum. And there are more general ones, more general relationships that we'll see that are true universally, in which case we get these universal constants. And those universal constants, like they apply to anything in the universe. And that's really where physics loves to be.
So what if I use like found the constant for like the BMR deer, and would I get something similar if I try plugging the constant for the deer into the L?
You should. It should fit really well. Now there's going to be variation between different mammals. Some mammals are going to be, slightly off. Humans are one of the ones that are a little bit further away from what you would get, but you actually end up with values that are relatively close to correct. Like, nothing's going to be exact, especially in the life sciences. If you're someone that's going into life science, you're going into science that there's a lot of variability between different species. But as long as you're dealing with a mammal, you should end up with mammals that follow this trend really, really well. Any other questions? All right, so then we think, well, what other physical quantities exist? What physical quantities exist? Because as we talk about these different physical quantities, we're going to want to understand how to build relationship from these quantities. So what quantities might we look at? We have base quantities, and we have derived quantities. Derived quantities are calculated from your base quantities. And we've already listed a couple. We've listed a couple of base quantities. We have length, we have mass. In lab, we calculated area and volume. Area and volume are derived based off of lengths. Said temperature earlier. Now let's think of some other things. These physical quantities are all things that we can measure, and we do measure. What are some things that we might measure? Someone yell out another physical quantity, another thing that we might measure. Any ideas? Something you measure. All right, let's think. Think today. You most likely have seen a number today, outside of lab. Outside of lab, if you have lab with me today, you've probably seen a number. Time, right? We all knew that we had to come to class today. Time is a measured quantity. It is a base quantity. What other things have we seen today, numerically? Speed, right? We're going down the freeway at a very responsible 65 miles per hour. Certainly no faster. We have our speed. What is that derived from? Well, if you think about the units, miles per hour, it's derived from length and time. Miles is length, time is hours. What other numbers have we seen today? We've seen distance. Distance is a length, right? Absolutely. Distance and length, they do differ in specificity, but we often say distance is the length between 2 points. What else do we have? Sure. A lot of us have probably seen today, maybe. We might have seen a voltage today. Or might have you seen this? Well, if you deal with electricity, you've seen voltage, right? Absolutely. What else have we seen? Well, today I got up in the morning, I stepped on a scale and it said, ouch. No, I stepped on a scale and it read out what? It read out how many pounds I am. Pounds is a derived unit. What is it a derived unit from? Well, we'll see. We'll see that later. But we have all of these different units, right? We have all of these different units. Do we have any questions about this? Any thoughts? Any questions, comments, concerns? You feel good about this? All these different quantities, yes. Oh, sorry. All right, so we have all of these different physical quantities. And more physical quantities exist than just these, right? Physical quantities exist beyond the scope of just these 8 that we've put up here. We were talking about this elephant and this mouse, and we said, hey, they were burning some amount of calories today. Calories is a unit of energy, so certainly that's a physical quantity. Again, the list goes on and on. We're going to stop here for our quantities because we want to move forward and we want to discuss how some of these quantities might differ. So we look at these and we say, some of these quantities might depend on directionality. What do I mean by that? When we talk about physics, it is often imperative that we take a look at the direction certain objects move, perhaps, right? So for some of these, direction matters. And for those quantities in which direction matters, we give those a special notation. Now, which ones might these matter for? We think about things that can have differing directions. Well, if we discuss, maybe going back to this idea of distance, it was measured earlier, or it was discussed earlier, right? We heard this idea of distance. Well, if I say that something is 5 meters to the right of me, that is vastly different than saying something is 5 meters to the left of me, right? So when we talk about distance, we say direction matters for distance because something being to the left of you is different than something being to the right of you. If you look to your left, you see one person. If you look to your right, you see a totally different person. What else does direction matter? Well, I was coming to work today, right? I was coming to teach this class, and as I was doing it, I got on the freeway and I made a decision. I made a decision that I'm going to travel south to come here. That would have been a very different. There would have been a very different result if I had traveled north. So I decided to travel south today. That means that my direction of travel played a role in where I ended up. We call that velocity. Velocity is the speed that you travel with an included direction associated with it. So we have this idea of distance and velocity. Both of these, direction matters. Now we look a little bit further and we say, I was coming into class and I approached the door and I tried to push it, but it didn't move. I tried to push it, it didn't move, but when I pulled it, it did move. What was I doing there? I was applying a force to the door. And I got a different result depending on if I pushed or if I pulled. Meaning the direction of the force applied gave me a different result. So, force seems to have a directional component to it. Again, if you do something in a different direction, then you have a different result. All right, well, all of these, direction matters, and since direction matters, we give them a special indication. We call these values vectors. Vectors are physical quantities in which direction plays an important role, in which we need to have some specified direction to understand what relationships will play out. Meaning, thinking back to relationships allow us to make predictions about the future. It allows us to make predictions about an elephant based on a mouse, right? It allows us to make a prediction about the mass of a block of aluminum. And in order for us to make accurate predictions with vectors, we need to know what direction they are heading in. We need to know the direction of our vectors. Now, these are different than other physical quantities. For some physical quantities, there is no direction. So for example, we have physical quantities that have no direction. What are these physical quantities? Well, time is interesting. They are called scalars, but what are some of these? Some of these are mass, right? Mass does not have direction. Mass is just a count of how much matter exists in an object. Temperature. Temperature doesn't have direction. It just tells you how hot it is outside. And time. Now time is interesting because in the case of this class, time doesn't have a direction because time can only technically move forward, right? We can't reverse time, at least not to my knowledge. If you guys figure out how to reverse time, let me know. But to my knowledge, time can't be reversed. However, if you delve deep enough into theoretical physics, you can start counting time as being a vector-like quantity. You can start talking about this direction of time's arrow and all this other stuff. But for this class, yes, we will absolutely consider time a non-directional quantity. And as was mentioned earlier, these non-directional quantities, these are what we refer to as scalars. And every value that we look at, every physical quantity that we see can be categorized into either being these vector or these scalar quantities. We look at something like voltage. Voltage is a scalar quantity because it just has a singular value. If you look at something like calories, calories is a scalar quantity. If you think about speed, now here's an interesting one. Speed. Let's think about speed. Where have we seen it today? We were driving to school again. We looked down at our speedometer. It says 65 miles per hour as we're on the freeway. Our speed says 65 miles per hour. Now, does it change if you drive north or south? No, it'll just read out that 65 miles per hour. Speed is considered a scalar quantity. Velocity is a vector quantity. Although these two things are very closely related, we ask the question, well, how are these two things related to one another? These two things are related to one another based on this idea that vector quantities not only have direction associated with it, but it also has a size associated with it. We call that a magnitude. Our vector quantities not only have direction, they also have magnitude. The laptop keeps shutting off. And so then we want a way to discuss these vector quantities and discuss these vector quantities in both terms of its magnitude and direction. Now, since we're pretty familiar, I think, naturally with this idea of distance and velocity, we're going to restrict our discussion of vectors to distance and velocity. But no, all vectors follow this same path. All vectors follow the same type of mathematics. And if you guys have brushed up on your algebra and your trig and your geometry, then you'll be well off. If you guys are a little bit behind on your refreshers of trigonometry, well then be sure to stop me if you have any questions. So, how can we represent these vector quantities then? Well, we might say here is your house, expertly drawn, photorealistic. This is your house, and you need to travel to school, which is some distance away, right? Well, let's say we want to travel to school. If we were to travel to school, we would start at our house, and we would travel towards school, and let's imagine that we could walk in that direct path. We draw this arrow, and this arrow represents the path that we have to follow. This arrow represents the vector quantity of distance. This arrow represents this vector quantity of distance. And we say, well, perhaps for me, this vector quantity of distance Perhaps for me, I live 10 kilometers away from school. In this class, we will typically use meters, kilometers, not miles, not feet. But let's say we live 10 kilometers away from school. What can I say? I can say that this vector quantity of distance has a magnitude of 10 kilometers. We look and we say, well, what direction is it? North, east, south, west. What direction was I traveling? Southeast. So I might say that this vector distance can be represented as 10 kilometers southeast. I'll be a little more specific than that, but eventually. But this gives us our basis of understanding. Do we agree? And then we can always say that if you start at my house and you travel 10 kilometers southeast, you will end up at school. You cannot end up anywhere else if you travel 10 kilometers southeast. Why is that? That's because your house has a definite location, school has a definite location, and the distance between those two locations is 10 kilometers southeast. If you travel a different direction, you'll end up somewhere else. If you travel north, you'll end up in a different place. You won't end up at school. If you travel 5 kilometers, you won't travel to school. You only travel to the location of school if you travel 10 kilometers southeast. Does that sound good? Any thoughts, any comments about this? All right, well, let's say our friend lives a little further away. Let's say here's our friend's house. Our friend lives a little further away, and they would have to travel, we'll say 20 kilometers. The distance for our friend to travel from their house to school is going to be 20 kilometers southeast. Do we agree? So our friend would have to travel 20 kilometers southeast. These two vectors share direction, but not magnitude. We'd say that these two arrows represent the two vector distances for our distance from home to school. But for me and my friend, these two vector distances have different magnitudes. Same direction, different magnitudes. Sound reasonable enough? All right. We look at a third. We have a third friend. We're so popular that we have 3 friends, and our third friend lives over here. And perhaps our third friend needs to travel 10 kilometers again to get to school. For our third friend, what is the direction that they travel? West. They travel 10 kilometers west. So us compared to our third friend, we have the same magnitude. In other words, we have to travel the same distance to get to our school, but different directions. So we share magnitude, but we have differing directions. That sound all right? Any questions, comments, thoughts, or concerns so far? So for any vector quantity, you need 2 things. You need a magnitude and a direction. And we can specify them by saying some vector d for displacement, distance, with a direction. Some vector d is given by some magnitude and direction. For example, we might say distance for person 1, the vector distance, and we're going to change our language here in a second. Our vector distance has some magnitude with some direction. And for me, traveling to school, I may say that's 10 kilometers at a direction of southeast. But I want to be more mathematical about it. I don't want to just say southeast. Instead of just saying southeast, I want to be more mathematical about it. And I want to say, 45 degrees south of east. What does that mean? That means you point east, you go 45 degrees south of that, 45 degrees down, and that gives you the direction. Now we have a numerical value associated. We have a numerical value associated with our southeast. And we can now differentiate maybe a 30-degree angle, or perhaps an angle that's a little bit steeper, 60 degrees, whatever it is. We have a way now to quantify that direction, to put a number to that direction. In physics, everything we do, we want to eventually put a numerical quantity on it. In other words, we want to quantify our physical values. And as we quantify our physical values, we can start to talk about different directionalities. But instead of using these directions, northeast, south, and west, we take another step into the realm of quantification. And we start to use not northeast, south, and west, but instead we use, here's our compass rose perhaps, north, east, south, and west. Instead of using north, east, south, and west, we use the mathematical Cartesian coordinate system. Cartesian coordinate system that says not north, but y, x, negative y for down, negative x for left. So y would represent north. East is represented by x. And this just gives us to our normal Cartesian coordinate system, where if we look at a position on our Cartesian coordinate system, we might draw out that coordinate system, 2, 3, 4, 1, 2, 3, 4. And we might say that we have some location on it, 1, 2, 3, 4, 1, 2, 3, 4. We might have some location in which the x value is 4 and the y value is 4. In other words, we might say this has x equals 4, y equals 4. And suddenly we have a Cartesian coordinate system that represents, instead of north, y, and instead of south, negative y, and instead of east, x, and instead of west, negative x. So we use our Cartesian coordinate system that I hope we're familiar with to some degree. Do we feel all right about this? Now, when we create these coordinate systems, it's often important to define some origin. And when we define some origin, that is telling us where we are putting our 0, 0. So when we define our origin, we want to define our 0, 0, and perhaps it's appropriate to say our origin is our home. That's where we start our day. That's probably where we end our day. So maybe it's appropriate to say our origin is our home. That sound good? And then we say, to get to school, I have to travel 10 kilometers to get to that location. 10 kilometers where? Well, 10 kilometers at a 45-degree angle. Do we feel okay with this? Any thoughts, any comments? So we travel 10 kilometers at a 45-degree angle. But then I ask the question, well, what is the positional location of school, right? We can say it has some x position and some y position. What is the positional location? Well, that positional location needs to be 10 kilometers from the origin at 45 degrees. How do we figure that out? Well, if we want the x component, we see how far to the right do we need to go. And if we want the y piece, we see how vertical we go. And suddenly, what do we have? We have a right triangle. Do we all see this right triangle? We all look at this right triangle. And when we look at this right triangle, we then ask the question, well, what is the distance we travel to the right? What is that x positional location? How do we find that? Well, this is where trig comes into play. Because what do we have? We have a 10-kilometer hypotenuse. A 10-kilometer hypotenuse and a 45-degree angle. We utilize our trig, right? We use our sines and our cosines and our tangents. Our sines, cosines, and tangents will tell us how far is it horizontally? How far is it vertically? And when we put these in, we can say that the opposite leg of our right triangle, the opposite of leg of our right triangle is going to be represented by the sine of the angle multiplied by the hypotenuse, right? Because the sine of theta is given by opposite over hypotenuse. So if we want that opposite leg, we take sine of 45 degrees and multiply it by that hypotenuse, 10 kilometers. And then we have cosine of theta, which is adjacent over hypotenuse. So if we want that adjacent leg of our right triangle, we take the cosine of 45 degrees and we multiply it by the hypotenuse, 10 kilometers. Everybody, take out your calculator. Take out your calculator. We are going to find the adjacent leg of our right triangle. The adjacent leg of our right triangle, well, that's going to be hypotenuse, 10 kilometers, multiplied by the cosine of theta, cosine of 45 degrees. Make sure that you are in degree mode on your calculator, not radians. Seven point what? 7.1 kilometers. 7.1 kilometers. So the adjacent side of our right triangle is 7.1 kilometers. You do the same thing for your opposite side, you'll find 7.1 kilometers as well. So what does that mean? That means that if you create a coordinate system to relate your house to your school, you would have that your house is located at the origin. That is home. And then you travel 7.1, 1, 2, 3, 4, 5, 6, 7, and a little bit extra. You can travel 1, 2, 3, 4, 5, 6, 7, and a little bit extra kilometers. And that gives you the locational position of school. School would be located at 7.1x and then negative 7.1y, right? Negative because we are traveling south, or negative y. Does that sound good? So what does that mean? That means that instead of traveling 10 kilometers southeast to get to school, you could instead travel 7.1 kilometers east and 7.1 kilometers south. Yes? 7.1 kilometers east, 7.1 kilometers south. And when we do this, we get the vector distance quantity, that tells us how far east and how far south we need to go. We end up at the same location. All right, are there any questions, any thoughts, any comments? Now we're going to change our language a little bit here. We're going to change our language because now we are going to say not vector distance, not vector distance, rather, and I've tripped up on my words here a few times and I've already used it. Instead of using vector distance, we are simply going to use the word displacement. Displacement is the physical quantity that tells you about the distance traveled and the direction it is. In other words, displacement is the term that we actually use to refer to our vector distance. Our displacement is our vector distance. And we can say that our displacement, the way we define displacement in this class, is that it only cares about where you begin and where you end. It does not care about what happens in between. What does that mean? That means your displacement does not care if you took the red path or the blue path. The displacement will give you the same result either way because the displacement just tells you what is the difference between where you started and where you ended. We'll talk more about that in a little bit, but yes.
Does it mean it also doesn't care about like speed or how fast you go?
Does not care about how fast you're going. Displacement doesn't care about how fast you're going because the school isn't getting any closer just because you're moving faster. The school stays the same distance away from you, so displacement is going to be the same. So if that's the case, then we can say that our vector displacement, yes, our displacement, d, can be represented as 10 kilometers, 45 degrees, south of east, we can also say this is 45 degrees clockwise from x, because if we look at our x direction, our x is to the right, 45 degrees clockwise, it goes down. Say this is 10 kilometers, 45 degrees clockwise from positive x. Or we can equivalently say our displacement is represented as traveling 7.1 kilometers east and 7.1 kilometers south. So we can say our displacement can be rewritten as taking the path of 7.1 kilometers in the x direction and adding to that 7.1 kilometers in the specifically negative y direction. So we did 2 steps, so we add those 2 steps together. And once we do this, we have now a well-defined vector quantity. And whenever we have a well-defined vector quantity, we'll put an arrow over the letter representing our vector to say that this thing has directionality to it. So this gives us a well-defined vector quantity. Now there is an issue here. X is a tricky term to use. Why is it tricky? It's tricky because it often is used for multiplication. And we don't want to confuse those two things. So instead what we do is we introduce what we call unit vector notation. So we introduce unit vector notation, where we say if we are moving in the x direction, x direction is represented with the letter I with a little hat on top. Call this I hat. So if you're moving in the x direction, we say that's I hat. And if we move in the y direction, well, moving in the y direction is represented as a j with a little hat on it. So we would say that our vector quantity, yes, it's 7.1 kilometers in the x direction, but it is also represented at 7.1 kilometers in the y direction. But more algebraically, we would write it as our vector displacement is 7.1 kilometers I hat minus, that minus coming from the fact that we are negative y direction, minus 7.1 kilometers in the j hat direction. And this is how we will typically represent vectors. This is in its algebraic form. This is in its unit vector notation. And when we're in this unit vector notation, we can start to use various vector algebra with it. We can start doing vector addition, vector subtraction, and how might we do that? In order to do some vector addition, perhaps we say that we travel some displacement d1 of 7.1 kilometers I hat, 7.1 kilometers j hat, that gets us to school. Perhaps after school we travel a second displacement, d2. And perhaps our second displacement is 3 kilometers I hat plus 4 kilometers j hat. And we want to do an addition. We want to see, well, where do we end up after we undergo these two displacements? Well, the total displacement is just going to be our individual ones added together. So we ask what happens when we add together our two displacements. When we add together our two displacements, well, that's just saying we take our first one, 7.1 kilometers I hat minus 7.1 kilometers j hat. And what do we do to it? We add to it our second. And we just use our algebraic rules. 3 kilometers I hat plus 4 kilometers j hat. We just add our two pieces together. Now, rules of algebra still apply. Rules of algebra specifically apply to these unit vectors. So what we're going to do is we're going to add together our like terms. We add together our like terms. Our like terms are our I hats. Our like terms are our j hats. So we take 7.1 and we add 3. What do we get? We get 10.1 kilometers I hat. And then we do negative 7.1. And when we add negative 7.1 to 4, we get negative 3.1 kilometers j hat. Sound all right? Now, if we were taking into account sig figs, we would round it to 10 and 3, right? But we're not going to do that because we're going to do one more step. We're going to do one more step here. And first thing we want to do is track our motion. So we start at school, we start at home. We travel to school. And when we do that, we travel 1, 2, 3, 4, 5, 6. Let me put a little bit of gap. We travel 7.1 to the right and 7.1 down. 1, 2, 3, 4, 5, 6, 7. Did not space those out well at all. Let's see if I can do a better job here. Coordinate system, we travel 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So we travel first from home to school, and when we do that, we travel along the displacement d1. Then what we want to do is we want to travel to our second location, and to get to our second location, we travel 3 kilometers. I hat means positive x. So we travel 1, 2, 3 kilometers to the right, and we are traveling 4 kilometers in the positive y direction. J hat means y, so we travel 4 kilometers in the positive y direction, 4 kilometers up. So for our second displacement, that's 3 kilometers to the right, 1, 2, 3, 4 kilometers up. And we end up at the second location, D2. So when we add together displacement 1 and displacement 2, this is our second location that we go to after school. Do we feel all right about that? Now the last question we might ask. If we wanted to go home, what is the displacement vector that takes us home? Well, the displacement vector is going to be 3.1 kilometers up and 10.1 kilometers to the right. Exactly what we got when we added them together, just in reverse. The negative from positive, positive, negative. That's because the reverse direction should take us home. So we have our final displacement vector. I'm going to call this displacement vector D3. And our displacement vector D3 should take us home. Well, if we should follow that vector and we want a straight line path home, let's try and figure out what that straight line path would be. We travel 3.1 kilometers up, and we travel 10.1 kilometers to the right. I want a direction we travel. Well, a direction is an angle, so we'll find theta, give us the angle that we have to travel home. And I want a distance we travel, and specifically a distance we travel if we travel directly home. If we travel directly home, we can find that displacement, d3. We can find the total distance from start to end that we have to travel. We can find that distance by taking, well, we have both legs of the triangle, so Pythagorean theorem. 3.1 quantity squared plus 10.1 quantity squared, square root of it. That gives you the hypotenuse of this right triangle. If we want the angle, well, we have both sides. And what trig function tells us about both sides? That's the tangent function. So we can say tangent of theta is opposite over adjacent, 3.1 kilometers. In other words, the angle is the inverse tangent of 10.1 over 3.1, and our units cancel out, kilometers over kilometers, and that would give us our angle. All right, well, let's calculate this out real quick. What do you get when you apply Pythagorean theorem? And what do you get when you apply the inverse tangent function? All right, raise your hand if you have the Pythagorean theorem part calculated out. What'd you get in the back? Yes.
I got
11. 11? Anybody else get 11 kilometers? Raise your hand if you got 11 kilometers. Wonderful, wonderful, amazing. All right. What did we get with the angle? You apply the inverse tangent function. What is it? 73? 72 points on all. We'll say 73. 73 degrees. 73 degrees what? 73 degrees counterclockwise from positive y. Why is it counterclockwise from positive y? Well, positive y is directly up. If we go 73 degrees from up, it's pointing in that direction. 73 degrees counterclockwise. Here we've found the displacement between where we are at and where our home is. And our displacement is a combination of magnitude as well as direction. So we do in fact have a vector quantity here, vector quantity of distance and direction that distance is in, giving us our displacement. So that's a brief rundown of vector quantities. Now, as we go throughout the semester, we're going to be doing this work over and over and over again. So if it's not like crystal clear at this point, don't worry too much about it. Because again, you'll get so much practice with these vectors throughout the semester. that by the end of the semester you'll really have this down. And when you deal with vector quantities, it's important to remember that all of these vector quantities relate back to triangles. Every time you're dealing with a vector quantity, you are dealing with triangles. Here is a triangle for our displacement d3. Here is a triangle for our displacement d1. Here is a triangle for our displacement d2. Every vector can be written as a triangle. And the first thing you should do whenever you have a vector is draw out that triangle. Yes?
Is it always going to be a triangle? Is this always going to be like the place of origin to start with?
Yes, and depending on what type of vector it is, that place of origin might be important. With things like velocity and speed, place of origin is a little bit more nebulous. It's not like super well defined, but something like displacement and position vectors specifically, place of origin is very, very important. And we'll talk more and more about that as the semester goes. But in this case, place of origin, well, kind of important. We have to define more about this. Any other questions? All right. So that's it for today. You should be able to work through your homework. If not, whatever is left over will be talked about on Monday. But you should be able to finish, I think, most, if not all, of your homework at this point. That is due next Wednesday. If you have any questions, feel free to stick back and ask. Otherwise, I'll see you guys next week. Have a good weekend.